On to calculus, tangent lines and new tangent planes. So we have our curve in space, we'll do lines first, and a point on the curve has t value 2. Now our new way of referencing it, we're going to have a vector that pushes from the origin to that point. There's our position vector, r of 2. There's the connection with the parametric form. Is the components of the vector are the coordinates of the point. We're plugging 2 into the parametric form, which describes every point on the object in terms of the parameters. Vector form, vector that points to the point. Take a derivative with respect to t. From Calc 2, we know this is the tangent vector. And now looking, pushing the green, then the blue, is about the same as pushing to r of 3. r of 3, 2 plus 1, which is approximately the green push plus 1 blue push. This is exactly a line construction. The tangent line in vector form, position vector, t, slope vector, and there's tangent lines. For tangent planes, we're going to redo this construction twice. There's a curve, just like we had, and a point on the curve. Got parameter value 2. Since it's a surface, we have another curve. Instead of s and t, we'll go ahead and say t1, t2. That other curve has its own parameters, so that same point has that parameter value 4. These two curves are embedded in a surface. For our vector description, start at the origin, and we'll push onto the point. Tangent vectors. T1 is varying, T2 is fixed at 4, and so it's just a function of T1. I take a derivative for the tangent vector. T2 is my variable, T1 is fixed at 2, and I take a derivative and get my tangent vector. We have a new notation for this, the partial derivative notation. Taking a T1 derivative, and I'm taking a T2 derivative. That way all the information's in one symbol. Point two vectors gives me a plane. Tangent vectors, tangent plane. Every point on the tangent plane I get to by scaling my tangent vectors and pushing them. Scale the first by S1, scale the second by S2. So the vector equation for my plane, push onto the plane, scale the first tangent vector, scale the second tangent vector. There's our tangent planes. Take a closer look at partial derivatives. We have a surface. That's one equation. Since I have a sum of squares, it's natural to use a triangle. And think Pythagorean theorem. Every right triangle is similar to the sine-cosine triangle, and I can use r and theta as parameters. Or in this case, I'll use t2 and pi t1. Doesn't matter the names. There's the equation form for our surface, one equation that all the points have to satisfy. There's a parametric form for my surface, built up in terms of parameter values. Once I got the parametric form, the vector form points to that point. The coordinates of the point are the components of the vector. Now let's go through what we did in the construction. I'll fix T2 at 4. But then T1 is my only variable, so this is just a vector function of one variable. Take a derivative, and that's my tangent vector from Calc 2. The notation is the partial derivative notation, taking a T1 derivative. Well, there's no reason to put in 4, I can just in my head think of T2 as 4. This is partial derivatives. I'm taking a derivative with respect to the T1 variable while treating T2 as I would a constant. That's the definition of a partial derivative. What's good for T1 is good for T2. I'm going to take a T2 derivative treating T1 as a constant, say